Next speaker is Damian Osajda.
Okay, thank you, and thanks the organizers and the attackers for coming. Okay, so yeah, so I will be talking about our joint work with Piotr Przytycki. Is the correct pronunciation, by the way? So from McGill. This is also correct pronunciation. I mean, correct Canadian pronunciation. Okay. Okay. So yeah. So this is the result basically, but I will state it again. So I will first explain all the notions involved. I mean, there are just two notions involved, but okay. So first, but let me say what are Coxeter groups once again. Okay. So Coxeter groups are. This is axiomatization or generalization of reflection groups. So let me define them in the following way: that you have a given finite graph. So this is a finite graph with labels on edges. So with edges labeled by numbers. So by numbers 2, 3, 4, and so on. So with this graph, we associate the so-called Coxeter group. I will denote it W gamma, or I mean, most of the talk will be about, I'll be denoted by W. So I want to give you this notation because it relates to the notation that we had for Artin groups. Actually, Artin groups are defined similarly up to now, right? So there is a strong connection between them. So this group is given by presentation associated to this gamma, which is that you take the set of vertices of the graph. So this is actually the set of vertices of our graph. And then you have some, so those are generators. So I will speak here about finitely generated groups. And then there are some relations. And let me write them down for a reason that you will see in a moment. So having two elements of your generating set, there is Artin relation that we saw already. So there is STS several times equal TST several times, when this number here is simply the label of an edge. So MST is a label on the edge between S and T. S and T are vertices of a graph. And then there is a second, there is a second relation. So this is one kind of relations. So for every edge labeled by MST, you've got this relation, but there is also relation saying that every element, actually, that every generator is involution, so that S square is identity is 1. So for ST in S. And in view of this relation, this Artin relation can be rewritten in the form that is usually used for Coxeter groups, which is that ST to power MST is 1. Okay, so this is the standard presentation for Coxeter group, and such groups are popular, let's say. And so examples, we should probably have some examples. So let me start with examples and then say why they are popular. So examples, okay, I mean, for getting examples, you just need a graph, right? So if you take graph consisting of an edge, just one edge, and with some label, let's say M, then what you've got is actually the, so the Coxeter group associated to this graph is actually the diedral group of order M or 2M. I do not know what's the notation, so let me say simply M. And similarly, if you have no edges, which sometimes can be, so if you have no edge, like two vertices, then you've got simply diedral group, infinite diedral group, right? So this is the simplest example. Furthermore, note that if this label is 2, then actually this means S2 equal 1, which means that they commute. So label 2 means commutation. So of course, if your graph has many 2s or only 2s, then it means that there is many commutations. Here is another example that is like more, maybe a bit more complicated. And this is kind of origin also of Coxeter groups, namely they come as, I mean, the first examples come as reflection groups, some reflection groups. And actually we'll see in a moment that all of them are in a kind reflection group. So if you think about Euclidean plane and the group generated by reflection in sides of this one small triangle. So this is triangle 45 degrees, 45 degrees, and 90 degrees. So if you think about group generated by reflection in its three sides, so you will get the group acting isometrically, okay, by automorphism on such picture, on such tiling of a plane, of a Euclidean plane, where you will actually, so this will be a group generated by reflections in all of those lines, because you can convince yourself that you can conjugate by these reflections this reflection to this reflection and so on, right? So this group, how it relates to this presentation, well, this is a group actually. So the group generated by this free reflection is actually the group W corresponding to the graph. So three generators, and then this relation, this commutation means that there is 1, 2, and the other 2 means that there is 4 and 4. So this is a group. I mean, group defined by generated by this reflection is actually this Coxeter group. Okay, and similarly, you have other groups acting by reflections on Euclidean plane. You have also, or Euclidean space, then you have group of reflections on hyperbolic space, and so on. And yeah, so such groups are interesting. Well, maybe, yeah, I do not have anything specific to say. Well, they are important for many reasons, but not only in group theory. So they appear like extensively in, for example, in representation theory. So they are closely related to Lie groups. There is, for example, classification of groups acting like this by reflections on affine space or Euclidean space, on hyperbolic real space. So yeah, they appear everywhere. And in group theory, I believe they're important because they give a lot of examples, interesting examples. So they are very well understood. For example, various properties of these groups can be understood by properties of this graph, and graph with labeling. So like dimension, cohomological dimension, or whatever, virtual cohomological dimension, or whatever. So and just because they are given by a graph, I mean, given a graph, you have a group, and it's quite easy to see when this group is infinite, and maybe when it is also then cut-zero or hyperbolic. Then it gives you a lot of examples with some properties that you can prescribe. So this is a rich source of examples. Okay. Okay, but before going further, let me. I need some technicalities about such picture, about those groups. So we will work actually on Cayley graph. So for us, X will be the Cayley graph of such a group with respect to this standard generating set. And here I will work actually with undirected Cayley graph. Meaning that meaning that vertices are of course elements of my group, and then two vertices G and GS are just joined by one edge, not by pair of edges, because for evolution you would have, I mean, in usual Cayley graph you would have pair of directed edges. Here you have just one undirected edge. I mean, every pair of edges is just replaced by one edge. And then for such a graph, for such Cayley graph, you have that if R, so if R is a conjugate, so if an element is conjugate of element of a generating set, then actually R acts like as, let me say, reflection on X. So reflection here means that so if R is a conjugate of S, then you can think that you have G and GR here. This is this is like a sorry, that you have. Okay, it simply means that you see a picture like local here. So it means that that your R acts like S here, right? Like maps this to this and this to this, and similarly all other vertices that are like connected. I mean that are further are also interchanged. So R acts here, and because of this we have kind of wall. So in Coxeter, in the Cayley graph in X, you see a wall, you see a parallel edges, and you can think about R acting such that it preserves midpoints of these edges. So midpoints of these edges of fixed point of R form something that we will call wall of reflection. So fixing a wall. So this is definition that I will denote WR. So sorry for this abusing of notation W here and W here, but this is a standard notation for Coxeter groups, and for wall I cannot find better notation than W. So this is what we use. Okay, so let's see example here for this group, because we will. So everything that will happen now will happen in Cayley graph, in fact, but for pictures I will use this this picture that is here. So how it relates. So of course I said that reflections here are element of a group. I mean isometry. So to see Cayley graph of this group here, it's enough to take as elements of a group. It's enough to take the barycenters of those triangles. So it means that one reflection corresponds to this edge. So if you denote this by identity, then all the reflections, all the elements of Coxeter group are points, midpoints of triangles, and Cayley graph here looks like this. So here is the square corresponding to two commuting elements, and here is the octagon corresponding to this relation ST, 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 and so on. So this is the picture that we should have in mind, and here you see the walls. So the reflections, I mean the walls of the reflection in this, I mean the reflection of this Euclidean plane corresponds, of course, to midpoints of these edges and so on, right? So, and this is the general picture that you have in every Cayley graph. I mean, in the Cayley graph corresponding to this standard presentation. Okay, so of course it can be more complicated. It cannot be related to any Euclidean space or any other space, but we'll work with reflections inside along the walls inside the Cayley graph, defined this way. Okay, so for this, so these reflections, this wall structure give us that we already practiced a lot during this conference, gives us the wall metric. So actually the graph metric on G, sorry, on W, on my group. So the metric on W as okay, I should say the graph metric. So graph from the Cayley graph, X graph metric on W actually coincides, is the same as the wall metric from the set of walls, exactly those walls. So walls corresponding to reflections. So in other words, and the graph distance between two vertices that you can think as the number of edges in the shortest path connecting two vertices is the same as number of walls separating them. So just to keep it in mind. And related to this is a theorem that we will need. It is a standard theorem for Coxeter groups, the so-called parallel wall theorem. So this was first proved by Brink and Howlett in 91, 93. Which says that for a group, there exists a constant such that for every element of our group and every wall, let's say I will denote it like this, WR, if the distance of an element from a wall is at least q, then W is separated from G by another wall. So the picture here is that if you have an element and the wall is really far away, then there is another wall that does not intersect this wall and separates this element from our given wall. Okay. So, and this constant depends on the group, but given a group, you have such a constant. Okay, does that make sense? Right. Okay, so we'll need this theorem. Yeah. By the way, I should maybe also mention at this point. So I will now finish for a moment with Coxeter groups. I will go to biautomaticity, but before this, let me also mention that Coxeter groups are very related. Are like base for other important objects that we study, I believe here, that are buildings. So about building, you should think that building is like made out of Coxeter groups somehow glued together. So the Coxeter groups are like apartments, are parts of buildings, and then you glue such apartments together to create something. Let's say we use the word thicker, and here thicker means that, I mean, again, they correspond to very symmetric objects like this tessellation of the plane, and thickening here means that you can have such planes meeting that, you know, there are like bifurcations along some edges, so you can have a copy also of the same plane but like bifurcating here, so you know, so like going here like this, so the other copy. So buildings are more complicated objects, but they are closely related to Coxeter groups. So with every Coxeter group you have many, actually there are some parameters, but you have buildings associated to this, and some of our results. Okay, actually our marine result will also apply to buildings, which are actually much more complicated, and their origins, yeah, they probably origins are from some algebraic number theory or whatever. Okay. Okay, any questions at this point? So now I should explain the second notion involved, which is biautomaticity. And yeah, so it also appeared several times during this talk. I will, or during this conference, I will have here the definition. Oh, I'm probably, yeah, probably it's all known. So I will remove it. So I will give definition of biautomaticity that we work with. So biautomaticity. Okay. So this notion was introduced first by, I mean, at least usually we refer to the book, Word Processing in Groups by Epstein. There is so many authors. Cannon, Holt, Levy, Patterson, and Thurston. And okay, and what's that? So a biautomatic structure on a group. So I define this biautomatic structure on a group given by, let's say I will restrict here again to finitely generated groups. Is a regular, I will explain in a moment, language. So language is just some subset of words, of finite words in our generators. So I will denote this language L. This is just a subset of some. This is supposed to mean finite words in elements of S, such that the following properties are satisfied that we will verify later for some specific language. So each element of the group is represented by a word in our language. Second, and two further properties are the so-called fellow traveling properties that we already saw in Jeremy's talks and maybe in other talks as well. So let me draw them. I believe it's easier to draw them than to write. So the first property says that there exists a constant such that whenever you have two words from your language representing G and GS, so this is this is generator, so it means that in Cayley graph, those are elements, those are vertices joined by an edge. So whenever you have two edges, so this is, sorry, two words in language, so this is some word for G in language, and there is another word for GS in language, so W. Then okay, so you should think about this, that the words have common one end and two other ends are at finite distance, actually definite distance 1 in this example. So then it says that there exists constant C such that at every stage the distance does not exceed C. So this is what's called one-sided fellow traveler. And then for the third, this guy is also the other sided fellow traveler, which can be drawn as follows: that whenever you have two words, so sorry, two elements, first is G, so I already draw the word corresponding to it, and the second word is SG, yeah, I mean everything is in a group, so I can of course translate this picture. Okay, so this picture I will translate in this way. So I will have S minus 1, which means that this element, that this word represents the word actually SG, right? Because if I just move it by S, this will go here, this will go to SG, right? So whenever you have such word, again, those are words in our language. And of course, sorry, in our language. And of course, again, here distance is 1 because this is a generator simply. Then again, you have here that there exists okay, so first you have there exists a constant such that similar behavior as here happens. So again, you have the distance here, the distances here are at most C prime. Okay. So yeah. So both of them, I mean, so to these conditions we refer as fellow traveler property or double-sided fellow traveler property. Yeah, so no, they are not. So I mean, what you do when there are, so you know, the paths are defined. I mean, you define the paths. You can define the path as parameterized by natural numbers, and then you say that you go from 0, 0, 1, 2, 3, 4, 5, and then when you here you stay. So here the parameter goes farther. So it can happen that you should count these distances should be also counted like this, right? Later, this is, they do not need to be the same. So in our case, our languages will be geodesic. Actually, okay, they will be geodesic, but it's still they can be shift by 1 in the length of the words. Okay, so is this definition clear? Excuse me.
Would it be possible just to say the same?
Yes, I didn't give definition of biautomatic group, right? So you want me to write it or okay? Yes, okay. So there exists a constant such that if you have two words, if you have two elements G and GS, and you have words from your language, then there is a bound. Okay, the distance between two corresponding subwords is bounded by C. And similarly, if you have two elements G and GS, G and SG, then the distances between subwords of the word from our languages are bounded by C prime. Okay. So now, of course, a group is biautomatic. It's biautomatic if it has any biautomatic structure. Okay. I didn't say yet what means this regular. This is also important. So this regular for a language means so I will now say only the slogan. If there will be questions, I can answer them later, maybe. Yeah, that is somehow easy part of the proof. So a language is regular if it's recognized by a finite state automaton. So what you should think about this is that there is some finite machinery that produces your language, and actually only the words that can be produced that machine are in your language, and you can also recognize them by this machine. Okay, so this is kind of algorithmic property, and somehow this part is rather geometric, and this part, as we saw, for example, in Jeremy's talk, can be verified also on some other complexes, not necessarily on calligraph, and this part is this algorithmic addition. So, I mean, there are interesting interactions between those two things. So, for example, for some groups, it's easy to produce such kind of combings, let's say, but that are not very regular, and vice versa. Okay. So, yeah. So, I should probably note here a lot of properties that biautomaticity implies, but I will not. I mean, there is, but what I want to say, what I want to stress is that biautomaticity, you know, should be thought as a very strong understanding of a group, because you really know how to go from one element to another. I mean, you can really know it in this automatic sense, meaning that there is a machinery producing you this path. And moreover, these paths are controlled. I mean, there are not, you know, whatever paths, but they are controlled. So there is a lot of algebraic properties implied by biautomaticity, but I would rather like to think about this way, that you really have a strong control. And actually, in case of Coxeter groups, as I told you, for example, very important, Coxeter groups are very important in representation theory, and actually there people do computations using some languages. So they really care what are the words. So I hope our language will be also useful. Yes, what's?
So instead of telling us properties of biautomaticity, mention one property of Coxeter groups that is that we now know because they're biautomatic, or
Yeah, okay. So for me, the main property is biautomaticity. Yeah. Okay. Okay.
Don't you automatically also, I mean, you said your normal forms are going to be geodesic, but then you automatically get quasi-geodesic from the regularity, right?
Yes. Okay, so yeah. So we have now the main like players. So as I told you, the Coxeter groups are very well studied. However, yeah, biautomaticity was not known for them. So this is our main result. So 3 is the results.
Excuse me, it was a major problem even as
Yeah. So yeah. So let me state the theorem. So this is by myself and Piotrek. So once again, Przytycki. And this says that Coxeter groups are biautomatic. Yes, so yeah, so adding to Danny's comment, let me say what was known before. So previously, and actually it relates also to my talk. So previously, so the previous episode, if there you were somewhere, so automaticity was known. So first, it was proved under some assumptions, so not fully, by Davis and Shapiro in '91, and this is under assumptions that the parallel wall theorem holds. So they actually didn't prove the parallel wall theorem, and then Brink and Howlett proved the parallel wall theorem, and actually they used the same language here. So note that, yeah, maybe I should note that. So there is some language, of course, for automaticity is some poorer sister of biautomaticity, and basically it refers it says that you have only one-sided fellow traveler. So so for this you also need some language. So Davis Shapiro introduced some language. So their language is not biautomatic. So language. So this language is good for automaticity, not good for biautomaticity. This is the same language here. And what I said, for example, for people about people in representation theory, that they are building some or constructing some programs or implementing some computations. So they, for example, use this language often. So today I will present you another language. Of course, we claim there it is better in many senses. Yeah, for example, for this. So biautomaticity itself was proved for some subclasses. So for example, for cubical, I mean for co-compactly cubulated groups, it follows from Niblo and Reeves construction. Then there were some special cases, in particular Zach and Piotr and myself. We proved this for two-dimensional groups, and there were some other works for relatively hyperbolic and other. So okay, it was known for some subclasses, for many subclasses, but here is our result is for all Coxeter groups. So yeah, what I said, let me remark it because it's important for our next corollary. So for proving this, for proving the theorem, we introduce what we call voracious language. I will explain in a moment. Okay, so this is a new language. Yeah, so you can construct a lot of languages, but it seems that not many of them gave biautomaticity. So we construct new language, voracious language, and this language has some interesting properties. In particular, one of them is that this language is invariant, is preserved by automorphism of Coxeter group, preserving the generating set. So if you have given this standard presentation of Coxeter group, and then you have automorphism preserving this generating set, that the language stays the same. This is, for example, not true for this language. And yeah, this seems like some very, I mean, I don't know, artificial property, but actually it has important consequences. So one corollary of our construction, so of this theorem, meaning the proof of this theorem by defining this voracious language, is that uniform lattices in buildings are biautomatic. So this simply means that here by buildings, I mean there are many notions of buildings, but the most standard are buildings associated to Coxeter groups. So for a building associated to Coxeter group, and this means simply a group acting geometrically on this building. So for groups acting geometrically on buildings, you have biautomaticity. And here, as I said, so the proof, I mean, the idea of a proof is that this voracious language has this property that is preserved by automorphism fixing. Excuse me? Yes, yeah, that's work also. Yeah, we'll see. I will define it. Actually, yeah, the truth is that the main difficulty in the proof is defining this language. Yeah, so the voracious language is preserved by automorphisms, preserving the generating set. So let me say this S. And so this property plus the result of Świątkowski, oh, I forgot, like 90 something, 2000 something. So this is all our work. I mean, we do not need to do anything more. We just, if you have language implying the language that defines biautomatic structure, and moreover, the language has this property for Coxeter group, then you immediately, by his result, has this property for groups acting geometrically on buildings. Okay, so now, as asked, I should define the voracious language, and this is, yeah, so this is actually the proof of the theorem. So any questions on the statement or about any attacks? No more attacks. I will, okay. Could you remind me 5 minutes before the end, and then, okay, so now, so the proof. Okay, so as I said, actually the proof will be mostly defining the language. If you when you define it correctly, then it works. It's not that uncommon, right? Right. Okay. So I will keep the notation. So W will be my Coxeter group, and then G will be elements of Coxeter group, and so on. So for G in my group, I define this W of G, this curly W of G, as the set of walls separating G from identity, but not separated, of course, by a wall from G itself. So this is like the set of the closest walls to the identity, okay? Sorry, to G. So let me give you an example. So this will be my running example for the definition of voracious language. Okay, so here will be my G, and identity will be somewhere here. Let's say here will be my identity. Okay, so what's WG? So those are walls separating G from W. So there is many like this and this, but this doesn't count because it is separated by this wall and also by this, right? But this one is not. So this is one example of the wall in WG. There is another example, this one. This is also like a closest. And there is another one, for example, this one, right? And what else? Is there an what? Identity is here. This one, right? Okay, so this is WG. So those are, once again, those are the closest walls separating G from identity. And then we have partial order on elements of our group. So we say that G prime is smaller than G if G prime lies on a geodesic G prime from identity to G. Right. So for example, this is a geodesic. So every element that I crossed is smaller than G. And for example, this element is smaller. This element is not smaller because so you can also see. I mean, okay. So in particular, by our description of a metric, to go. I mean, if you go, I mean, if you are on a geodesic, then you have to be separated from G or from identity, right? By some wall. I mean, there is no wall separating you both from identity and G, right? This is also a definition. Yeah. But separated mean, I mean, you can be separated only by walls, right? Does it make sense? No? Okay. Yeah. Once again, this WG is like the set of walls separating from identity, but the closest ones. And then we have a crucial definition. Okay, we have a crucial set which is P of G, and those are all elements G prime, such that G prime is smaller than G, so lies on a geodesic from identity to G, and G prime is not separated from identity by a wall, let's say W in WG. So in other words, you can translate it as all words from WG separates G prime from G. Okay, because they do not separate G prime from identity. Okay, so let's see what's that. So those should be elements that are on the geodesic. So we saw nearly all of them. And then they should be separated. They shouldn't be separated by WG from identity, right? So, but you saw all the walls from WG, these guys, these orange guys. So for example, this guy is separated by vertical wall from identity. So actually what you get here is this segment. So this segment in this case is P of G. Okay. And now the main point and the main theorem, okay, one of the main result here to define that will allow us to define the language is that PG has a largest element, largest with respect to this partial order. So our proposition PG contains largest element. Okay, so I want to give you a hint on the proof of this. Yeah, I mean, maybe not the whole proof, but main steps of the proof. But before this, let me show it to you, and then let me tell you why do we care. So in this case, of course, this will be the maximal. This will be the largest element, right? So those are all elements in this green part, and then you take the one that is the farthest from identity or the closest to G, right? So this is the one. Okay, let me call it now because I have this color. So this will be called P of G. So actually, before proving this, let me say that this is how we define our language. So definition of the voracious language. So voracious language. So I do as follows. Okay, I need to know something before, but let me say it to have some motivation. So I have G. I have my identity. I want to produce some word from G to identity or from identity to G. It's okay, some word representing G. So what I do, I look at PG, and then here between G and PG, I choose any word. So this is W, let's say W1. This is any word, any geodesic word. Okay, and then I go further. So here I take again. This is element of a group, so I can do the same construction. This is like P of G. And then again, I pick here any geodesic word, another geodesic word between this and this. And I go on. So now there will be lemma in a moment that the distance, that there exists a universal constant such that the distance between G and PG is bounded by C. So it means that I can define a path from G to identity by some up to some error, up to some definite error, and this error is finite. So actually, I have finitely many choices for this. So this corresponds to the fact that those guys are these guys are chosen. Are determined, like the choice is deterministic, and for the others, I can take all the choices. So this will give me a language that is really still well defined, like regular. Okay, so this is a definition basically. Of course, for this we need this lemma, but this will come in a moment because I need still to define other things. Okay, does that make sense? So yeah, so basically that's it. Now the only thing that we have to do is to check the properties. So check this fellow traveler, and regularity. Regularity is quite easy because it's, yeah, you will see that, you see that the definition of this PG is quite, depends only on a finite set of walls. I will comment on this maybe in a moment. This depends on the parallel wall theorem. And then here you have only finitely many choices. So this is also regular, let's say. So the only thing to check actually, if you believe this is the fellow traveler property, double fellow traveler, okay?
You always end up with a global, like a geodesic map.
Yes, yeah. So here, yes, that's correct. Yes, yeah. These guys, by definition, this guy lies on a geodesic from G to identity, and then here I choose the geodesic word. Yes. This is what we call voracious projection. Yeah, I should say maybe of G. Yes. Yeah. So you simply project in this voracious way and project. So yeah. So once again, here first I should go from here to here. Between them, I choose any word, and then I go farther again, projecting in this voracious way. So, yeah, let me. Yeah, I mean, I chose this example because it says something. I mean, this shows some, you know, so some properties of this language and why we called it voracious. Because, I mean, usually, I mean, what people try to do, or what's done in some examples in these other languages, is that you somehow, for finding the next element, you try to like cross the closest walls in a sense. So here you do the same, but this closest is defined in this strange way. So you see the distance here is quite big, right? You need to cross many other walls, for example, this and this also, to get here. So this is why it is called voracious. And actually, even on the plane for affine two-dimensional group, Coxeter groups, you can see even that you have to go really far away. So sometimes the distance is like 12 or something between between the element and its projection. So this is why we call it like this.
Little g, but it depends on the group.
Yes. This C depends on the group. Yeah, that's correct. Okay. So now, what? Yes. This element is unique. Yes. Okay. So now I will define. Okay. So basically that's a proof. I mean, I didn't prove the fellow traveler, but before this, I wanted to give you some more details. So, okay, so you can see it as a proof. And now let me get to make my hands dirty, really dirty, and to see some nasty details, but still not the most nasty, right? Okay, so actually this proposition that PG contains the largest element. So when we proved it, we found out that some other guys, actually from Montreal, from UQAM, from Université de Quebec, were doing similar things. They are doing Coxeter groups. They are working with Coxeter groups from some totally different perspective. So there is the so-called bipodality lemma. So I want to state it because it's the way of advertising their efforts and give them credit. So we didn't know about this. We proved this lemma, and then we found out that actually Dyer and Matthew Dyer and Christoph Holweg. So Christoph is from UQAM. In 2016, actually proved this. So what they prove is the following. The proof is the following. So this is a lemma about actually about finite Coxeter group, or So is the following. So suppose reflections R and Q in our Coxeter group. So those are conjugates of generating elements, are sharp angled. So let me explain this. So sharp angled means, so you have two reflections like R and Q, and sharp angled means basically that so with those two reflections, okay, they should, first of all, they should, they should be of finite. I mean, they should have a finite exponent. So there is a finite group generated by them. So the group RQ is finite, and then this is finite diedral group. And then when you take the reflections, and when you take the walls corresponding to those elements, so WR and WQ, then actually the walls define the fundamental domain of the action of this group. So this is why it means sharp angled. So they are, you take in the group generated by R and Q, you take the closest ones, closest reflections, and moreover, they shouldn't commute. So also we assume that R and Q do not commute. Okay. So for such reflections, and so suppose we have reflections, we have reflection on Q, and the wall U separating G from WR, so from wall of one of the reflections or from the wall of the second reflection. So then I will draw it in a moment. Let W prime be a wall different than them, so WR and WQ, but be a wall corresponding to an element of this diedral group, to an element of this group RQ. Okay, so I should probably make picture at this moment. So the picture is as follows: that you have two sharp angled reflections. So this is WR, this is WQ, and then you have a wall that separates our G from one of them. So yeah, so it can, yeah, so there is a wall U prime. Then the statement of the lemma is that for any other wall being the image of those two walls by this diedral group, so for any other wall, but not being one of them, so for any, not being the one separated actually, so not non-separated, sorry. So for any other wall W prime, there exists there is a wall separating W prime. There is a wall U prime separating W prime from G. So any other wall in this residue is also separated by some other wall U prime. So this is a lemma that is somehow crucial for the proof. And now just an idea of a proof of proposition using this lemma is that we want to choose. So I just remind you that proposition says that there is a maximal element in this PG. So having any elements, two elements of our PG, we want to find an element that is bigger. So we want to find, so we choose a path between them. And by definition of our set PG, this path, I mean, the walls in this path are not inside W of G. And then we want to find an element that will be bigger from both P and P prime. And we do it locally. So if the picture looks like this, meaning that like if this is like a height function, the distance, then if you have minimum, then actually what you do, you apply this bipodality lemma to those two hyperplanes, to those two reflections, and you find in the residue, I mean in the residue of those two reflections, you find an element that will still be in PG and will be closer to G. So this is how this kind of local lemma, because it's about two reflections generating finite group, how it applies to our proposition of finding the maximal element. Okay. How much time do I have? 5. Okay. 1 minute? Yeah. Okay. And I choose. Okay. 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 So that's the proof. That's the proof that the language is well defined. And now let me just quickly. So and actually this is the main problem in the theorem. I mean, it is our main, let's say, effort to define this language. So now you know how to define. I didn't prove that there exist constants such that distance from any element to its voracious projection is bounded by this constant, but there exists some such. So this relies on the parallel wall theorem. So if you remember, if I want to go from G to PG, I have to find the set of closest walls, right? So yeah, so this, I mean, the projection, the voracious projection is not too far from this. Of course, corresponds to the fact that if I'm very, very far, then any wall separating both of them we'll also have like a twin. I mean, we'll have wall that separates it from G itself, right? So this is how it comes to play as for this statement. And now this statement is, if you think for a moment, it's actually very close to at least one-sided fellow traveler, because what we then prove is that having two elements, as in this part 2 of definition of biautomaticity, you have G and GS, and you want to bound the distance between words corresponding to these two elements. Then actually what we do is that having such situation, one of them should be on the geodesic from another one to identity. So the situation really looks like this, for example. And then you actually show that if you take P of GS, then it's closer to identity than G, and actually it goes in this pattern. So this, and this, meaning that the distance between any two, between any 2 points here is bounded by this lemma, and hence also the distances between corresponding points in the voracious language. And of course, what's happening between is bounded because we just choose geodesic words. So this is one-sided fellow traveler, just depends on this lemma very easily. And actually the other sided fellow traveler, in the paper for a proof, we use the fact that you have a rich structure of a Coxeter group. So actually the other fellow traveler is by reflecting the path along some wall. So I will not get into details. I should probably stop here before attacks. Okay, thank you.
Were there theoretic consequences for the building result? For polycyclic groups?
I don't know. I don't know what's known, I don't know.
Does it have anything to do with like the group? Like, does it mean anything if it's really big or if it's small or something?
What do you?
Speed.
This has, for example, to do something with, for this in this affine or in this like real case, it has something to do about the angle, for example. If this angle is very small, then you can really, this projection is really, really far away. So this is one dependence. I do not know. We didn't extract any particular dependence. We also rely here on the parallel wall theorem. So there is also something buried there. I cannot say anything more.
For the dual cube complex with co-compact, how is this language related to the simple use?
This is actually the same language. Yeah. Yeah. So actually what we do here, so you probably see it, but what we do here is that we find some paths actually in, so every Coxeter group has this big K0 cubical complex, defined by these walls. The problem is that this Coxeter group doesn't act co-compactly. So what we do, in fact, to some extent, we take, it is not exactly true, but this is, we take this big complex and we find Niblo-Rives paths there, but we cannot do it. We do it like step by step. So we pretend we are doing Niblo-Rives path, and then we project to our complex, and then we project, and then we do the same. So this definition of voracious projection is that you have to cross the closest walls. So closest walls define you the cube, like the. Yes, exactly. Yes. So we have to. So somehow we cross all these walls and then you project. So okay, we didn't try this. Yeah, by the way, I probably should also mention Mireille, right? That she also, there is some further work, so she used it for some other groups, right? Oh, okay. For dire groups, no? Oh. Okay.
Yeah, let's say more questions for coffee break.
Thank you.